Okay, so this is part 2 of our chapter, and this is chapter 14. And what we see, so the title of the chapter is comparing several means with one-way ANOVA. Okay, so what we seen is basically how to, last week what we seen is basically how to calculate ANOVA step by step without using a function in R. So we calculated, we made some consideration and then we finally calculate. So we thought what is ANOVA and built ANOVA from scratch. So now we are going to test some available function, and then also we are going to have a look at some p-values adjustments when this is happened, and it's going to be, so this is necessary when you want to compare more than one, so you do more than one test, okay? You do like a certain number of tests, so you need to adjust the p-value, because otherwise it may be not that right in providing the overall picture. Okay, so basically, so we went through several tests, and then finally what we found is that we basically calculated the F test, okay, and we found this value, which was 18.61, okay. So this is our one-way ANOVA, okay, test value, the result of the value, and now we are going to have a look at this this result more closely and testing with functions. Okay, so the first function that we I show you in the chapter, chapter 14. Okay. Okay. So the first things that we do is so we had a look at the effect size. And okay, so we haven't done the effect size. What we did basically, so we left about this point, okay, using the ANOVA function, running the ANOVA. So we end up here. So this basically was our F test, and so we made this F test with 2 and 15. That was equal to 18.6. Okay, and so now we like to have a look at the p-value. Okay, because without going back on what we did. Okay, so in order to test the p-value, what is the p-value of this F test? We use this PF function. Okay, this PF function is basically the distribution of F. Okay, and so it's a distribution function, and what does is basically releasing the value. Okay, releasing the value of the P, provide us with the p-value for our case. Okay, so we can see that running this function here with our f, which is our ANOVA, so the main test value. We establish the degree of freedom 2 and the degree of freedom of 15, as we said previously, okay? And then we need to specify lower tail false, because this is one way ANOVA, not two way, this is one way ANOVA. And so if we run this function, we found this 8.65 e to the minus 05, so means a very low number, okay, close to 0. And so we want to see if this is our p-value. Okay, this is a way to just calculate the p-value of the f-test, as shown in the chapter. And then what we do is putting this comparing this to be less than 0.05. And so this is true, but we already see from here. So that means that our p-value is lower than our cutoff. And so we can safely say that we are going to reject the null hypothesis. Okay? Yeah? Can you hear me? Smeralda?
Yes.
Okay.
Yes, the only thing I was mute, but yes, I can hear you well.
I'm not sure if you can hear me.
Yes, I can hear you well, very well.
Okay, great. So
I am
now,
following.
say it again.
I am following.
Okay, great. So all that we've done, all these step-by-step things that we've done can be safely skipped by using the ANOVA function. So there are different types of ANOVA functions that can be used, and they are provided within different packages, within R and so on. So one is this one, AOV function. If we do this AOV, so we can see that this is fit an analysis of variance model in particular. Okay, you can specify the things, provide a wrapper function. This is a wrapper because you know what is ANOVA, no? Okay, we are comparing two. Basically, what we do is doing a linear regression on doing two linear regression model. Okay, and the result of this model, the variance of these models are compared, and then the result is the ANOVA. So this is now, so this provides a wrapper function to the linear model for fitting linear models. And then the main difference from VLM is in the way print. Okay, so we do the difference. Okay, so this is an object class of AOV or LM, so we can use the summary function to see the result. Okay, let's go and have a look at it. So if I do use this function now, okay, this is what's happened here. So that's our bias. What we're discussing here is something else. Okay, now we are going back to the mood gain and the drugs. Okay, here we were comparing, this was within the clinical trial, so we were comparing the drugs effect. So one placebo and two different drugs. here is another thing. This is the effect of the drugs on the mood. So we are now having a look at this on the drug, okay? And so this is the way we use the ANOVA, okay? And so this is the value, which is positive, okay? Because we are comparing more than one thing. And the residual standard error is about 30%. We can use the names function. And so we can see that two things can be extracted by this thing. And so we can safely use the summary function. And so here we have all the results that we been searching for. So this is the value 18.61, which is the F215, okay, that we did it here. This one here that we calculated. And then the other one is the p-value. So now all the steps that we did it are just done with a function. Okay. And that's it. So we do a summary, and so we have this fact. Now, what's happened is that we can do other things. Okay. So, for example, okay, this I'm not going through all the things because they're quite so straightforward. One more thing that we might need to think about is the size. Okay, so we know that we calculated the sum of square, and so we might want to consider what is the proportion of these two. Okay, so and so we can understand what is the effect size within our data. Then we can even square this effect to have an idea. And so then this is what we did before. So we know that the sum of square of the two, okay, is the total, so that we can calculate the effect size this way. Okay, this is squared and everything. So why we do that? We do this because we want to understand if, because you are not just comparing placebo to drug A, okay? You have placebo, drug A, and drug B. So you, if you want to have an idea of what's happening, so basically what you do, you want to investigate the relationship between two groups, okay? And you have three elements to compare. And so you are going to do placebo with drug A, placebo with drug B, and then drug A and drug B together. So you are going to do three tests, okay? So we like to have an idea if all we are doing is fine. So you can imagine that you now have just three, but you can think about doing more tests when you want to compare more things, okay? You do. And so for multiple comparisons, okay, what's happened is that the best, we already rejected the null hypothesis. Then the mean of a placebo, the mean of drug A, the mean of drug B are all equal. Okay, so they're not. So we already rejected these things. But we like to investigate a bit more. And so we run a pairwise t-test on each couple, okay? And so we do drug A and placebo, and we can run a t-test. And then, and this is one, and then we can do it with drug B, and then drug A and drug B together. There is a way to do this with a pairwise test. So, okay, so we can do it with this post-hoc pairwise test. We put inside our ANOVA results, and so we can see what is the value of the relationship between placebo and drug A. Okay. Then this is just one value, so we can see that if we compare placebo with drug A, the relationship is positive. If we and so all of them are positive, but we can see that with drug B, it's less than with drug A. So the relationship between placebo and drug A and the relationship between placebo and drug B is different. But you can imagine you have more to compare. So what we do is, what the best way to do this is correct for multiple testing. And there are two ways to correction that can be used. The Bonferroni correction, which is this one here, and then the whole corrections. So why we do this? Because we have more than one p-value. Okay, so the first correction with Bonferroni, basically, if you multiply the p-value times the time that you want to do the test. So in our case, for example, we have 3 tests, okay, for each couple. This p estimated, so our q, this is generally called a q value because it is not exactly a p-value. Okay, it's an adjustment. It's times our p-value. Okay, and so our new estimated p-value, which is now here called p estimate, but generally called q, has to be less than alpha, as in general is. Okay, but our alpha, can our alpha be always the same, like 0.05, even if we are testing, I don't know, for multiple p-values? That might not be correct. Okay, so we need to test, so consider an adjustment of the threshold, so the value cutoff, to which we compare our new q value or p estimated value, this p sign estimation here. Okay, so we need to consider an alpha, which is proportionate to the number of tests that we are going to do. Okay. Obviously, all those things are done with a function. Okay, so so we can use, for example, this post-hoc pairwise test with our ANOVA, but then we specify the method. So we can see that things slightly different, okay, but in substance, they are consistent, okay. Then what's happened? Then if we have more than just 3, if you have many more, okay. So our adjustment has to be adjusted again. Apply an adjustment on the adjustment, okay. And so we can use the Holmes correction with an iterative algorithm. And this iterative algorithm, what does is, imagine you have 100 tests, okay? So this J value goes from 1 to 100, okay? So each time you times the index of your p-value times your p-value, the first one, so you like J1 times p, your first p-value of the first comparison, and then 2 times p-value 2 of your second comparison, and so on and so forth until you reach the 100, which is the overall number of your comparison p-values, p-value. And so each time this new estimation is will be used as new value, and so iteratively you have a list. So everything is done again with a function. So like you have a p-value. This is the raw p-value, okay? So that is released by ANOVA, by one couple comparison, whether it's a t-test or f-test. It depends by the size of your data. So you have a 0, 1, 0, 5, 19, and blah, 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 blah. This is the rank. And this is times this. And so this is the new P that you are going to use. Okay. To make things clear, you use the function, but with a specification. Okay. Which is 15. Okay, let's have a look at this. Is that was 45, and this was 15. So you basically in this case, pairwise t-test and post-hoc pairwise t-test have the Holmes, so you don't need to specify this. To run the Holmes correction, you could specify method Holmes, but since it's the default, so you don't do it. So by default, it's Holmes. Okay, it goes iteratively or using each one. So it's a bit tricky to visualize, but there's other resources that might be able to let you visualize what's happened effectively. But in general, if you think about the basic one, so the Bonferroni, this is then this is the starting point when you have a small m. When things are great, so when m is larger, you start making a filter adjustment. This is basically what's happened. Then, okay, just to finally have a look at other things that we can do is basically there are other tests that can be used, and these are why all these tests and why all this, just as a confirmation. Okay, you can think about this future test as a confirmation of your initial test. You do ANOVA and you do eventually the correction if you do multiple tests. But then you want to have a look at to want to have a double check,
right,
about normality, homogeneity, variance, and independence. Okay, so yeah.
Can you hear me?
Yeah.
For example, this correction test, the Bonferri and Holmes test, they are only when we are doing pairwise comparisons, right? Like, for example, because we have more than two groups, we can have, like, I don't know, as you mentioned, 100 different groups. It's only in these cases, right? When we have more than two groups, or
Yeah.
right? Yeah. Okay.
Yes, you don't need it if you have two. If you are investigating one, you have one predictor, okay, for example, drug, but these are so it in terms of categories, and then you are it depends by how many value. Okay, in this case, you are going to test 3 p-values because you are going to investigate 3
treatments, or
yeah,
there are 3 comparisons, 3 pairwise comparisons.
yeah.
Yeah.
This is interesting because if you think about it, does linear models, so linear regression, but think about that this is a classification. So they not, so they are factors. Okay, so I have drug A, drug B, and placebo, drug A, and drug B.
Yes.
And so I'm doing a linear model with 2 of them. I'm checking the mood. I'm doing the mood. What I'm doing is I'm investigating the mood when influenced by a drug. Okay, but I have 3 types of drugs. One is placebo, one is A, and one is B. So I do a linear model on the mood and the drug in general, but it's not enough to me because I like to see which one of the 3. Okay, so I want to go inside it. And
yeah, but for example, why, I don't know if this is like silly, but why, if we have more p-values or comparisons, why increase the risk of committing error type 1? Why, if we have more p-values, there is a bigger risk?
Because you have more p-values, but you haven't considered the size, the effect size.
Right.
If you have one p-value, Okay, you might want to do the average of all the p-values, so you have an average, but that's basically the first adjustments that you can do. So you have a list of p-values, you do an average, and so you have a first adjustment. But then it might be so consider. So you might want to do a better adjustment than just an average. And so you do a proportion. Basically, this is what's happened. So you take each p-value and you multiply that for the size, but that effect size can also be adjusted by your cutoff.
All right.
Okay, it's an adjustment because at the end of the story, so if you you use it as a confirmation of your initial results.
Right.
And the larger is the number of p-values, the more important is the adjustment. So you now imagine you have 100 p-values, you do multiple testing, then this values need to be further adjusted. And so there is an algorithm that iteratively gains some like information from the previous p-value and then pass it to the other one and then pass it to the other one, then pass it to the other and then release the average, basically. But reproportionate to the size, which is not always the same.
Mm-hmm.
This is basically what's happened. And
Okay.
obviously, when you apply, when you do it step by step, you see clearly what's happened, but you have a function, which is a wrapper of all the steps.
Mm-hmm.
And I think I went, what I also wanted to show you that there are, so basically just to summarize, okay, so we do the F test when our sample is very small, okay, it's lower than 30 observations, lower than 20 observations, I'm not sure about it now. And then otherwise you do a T test, which on all observation releases one p-value. Then if you are investigating a factor on a factor predictor, which has, let's say, a certain number of levels that you want to investigate on your response variable, on the effect of your response variable, how it varies on the different classes of your predictor. Let's imagine you have a factor, a predictor, which is a factor, a fundamental factor. So you might want to investigate each one on the response variable. And so you do multiple testing. And the one-way ANOVA need to be boosted, okay, with an adjustment. And so you are going to use some adjustments. Then you, and so I think this is, there are other tests that we haven't mentioned. So there is a Welch test, one-way test, and the so this was then there's the cursor test. Let's open this up better. And so we end up the chapter going in reverse. So there is a other tests that are basically used to verify your results. And as we said, we need to check for normality, homogeneity of the variance, and independence. So to check for the normality, you use you do the Q test, the QQ plot and you see if it's like, where is it? Okay, so and then you run a Q norm. So you draw a QQ plot to see whether to check the normality of the relationship. As well use a Shapiro test. And this will tell you if it's the case to consider your data under a normality assumption. And then there are other tests to check the residual sum of square. And so to check the independence. And the other tests. So this one here are safely done with the function. And what you do, these are just a confirmation of your initial results in case you have doubts. Okay, and then you check it again. This one, for example, was on therapy. And so if we basically, for example, use this Kurzweil test, and we can see that this is basically specifying a chi-squared value and a p-value which is lower than 0.05. And basically the chapter shows how to use, how to make the test. And so we can do it this way, or specifying the data as we did it before. And it says that this provides the same results. Okay, so this is the test done step by step as we did it with the ANOVA. And then looking at the effect of therapy on mood. Okay, that was interesting. So I think we can go forward.
Okay.
On the other chapters.
Yes.